Hello, everyone. This is going to be Lab 8. Today, we're going to be talking about the chi-square and one proportions test. Okay, so let's see what we have here. First of all, it's very easy in R to introduce a contingency table. The example that we have is with the vaccinations and autism that I mentioned in class. So first of all, we want to tell R, hey, this is the appropriate table. It's very, very easy. You could use the creation of a matrix, as we call in R, where you basically specify which values you want, and they'll go like in terms of columns. So you say 440, 240, 184, and 584. So it goes like this. You tell it how many columns you need, in this case, 2. And then you can even put dimension names. So you can have autism with yes and no, and vaccinated with yes and no. So the syntax basically is this little code here. Let's plop it into our little code there. So once again, you have to tell it what you want to have in the dimension names. This is for, I believe, the rows, and this is for the columns. So let's go ahead and run this. You will see that it pops up here as a matrix, and when we open it up, it kind of looks like this. Let's make sure that it matches the one that we have, and yeah, it is 184 and 548. Okay, so you can put whatever you want in terms of the names here, but since we're just going to be doing a little bit of analysis, I don't pretty much care. All right, so what do we want to do? We want to run a chi-square test as we learned in class, and it's very, very easy. You have to just take this name and apply chi-square test to it. If you just write chi-square test, like so, you're just going to get the output. And there you go. Here's your p-value, right? 0.23. But if you want to save everything and review it a little bit more, it does make sense to try to, name it something. And then if you notice closely, when I do this little thing, I get more information than just the corresponding p-value and the chi-square and all that. So if I select this part of the code and run it, what it's going to do is it's going to run the chi-square test on line 7, as you can see, and then it's going to save it as a result. And if you just click on that result, you'll see again the same response as before. Okay, so this you don't lose any information, but right now you can also get the table of the observed values just to make sure that you're back in the right track, and also the expected values that you mentioned in class. So this is just basically a list inside the response results, and these are the theoretical responses that you would get if the two were independent. Okay. So once again, we look at the corresponding p-value, and obviously the corresponding p-value is much larger than 0.05, so we fail to reject the null hypothesis. The dataset does not provide enough evidence to just claim that autism and vaccines are dependent. Okay, so these two are probably independent. Okay, and since we've done this experiment multiple times over multiple years, we can safely say there's no connection between vaccines and autism. All right, so how would we then be able to do a similar analysis, but now we have raw data? So what do I mean by that? Look inside the Lab 8, and we have a little questionnaire. This questionnaire is basically something that I had asked the previous class of mine. Similar questions like the ones that I've asked you this semester, which, by the way, if you have a little bit of time, try to fill in these questionnaires. And in this situation, you basically have questions, and the columns corresponding to these questions can be thought of as random variables, and you have two random variables with multiple responses. Both variables are factors, and what we want to do is we want to create first the contingency table without doing any sort of counts. For some reason, this is not popping up for me, which is all right. What I'm going to do is I'm going to read it into R and open it from there. So if you have the questionnaire.csv at the same folder as the one that you're working with, and go sessions, set working directory, source file location, and just put then the line of code here. I'm going to read the CSV questionnaire, and I'm going to save it as a questionnaire. All right, so the first part was for the vaccines. This is just kind of reading it in. And notice that in this case, I don't need any packages yet. If we need some, we're going to add them later. So let's go ahead and read in the questionnaire on this piece of code. For some reason, it takes a little bit longer to read it in. It shouldn't be. It's very, very small. I don't know. There we go. Okay. So what's in this questionnaire? As you can see, you have a grade, we have book. Oh, and I see there's some column left over here. Not sure what that is. I'm going to work on that a little bit. But anyway, these are the only two columns that I care about. These are the possible grades, right? And these are the, whether or not you read the book. And we're trying to figure out if there's any connection between the two, but we have like the raw responses. What we need to do first is we need to create the contingency table. And to do that, you just, utilize the function table inside basic R, and I'm going to save it as Q, right? So this one is going to create a table between the two columns, the column grade and the column book. Let's see, this is not copying it right. Okay, you can just type it in. So Q for me is going to be table, and I'm going to put questionnaire, and then the column would be, oh, I don't know, what's the name of the column? Book. Oh, there it is. Popped up. I don't need it anymore. Okay, so it's grade and book. So you can just do questionnaire grade, comma, questionnaire book. Okay, and what this is going to do is it's going to create a little table here, which you can view if you just put its name down and select it and run it. Okay, so there you go. So these are the possible answers of proposed assumed grades, and these are whether or not the people use the book or not, and we're trying to figure out if there's any connection between them, right? Okay, so let's go ahead now and continue with the analysis. What you can do then is you can write a chi-square test straight up. And there it is. Just apply chi-square test to the table that you had before. And if you want to see the result, type result again and run it. Okay, there you go. Now, don't worry about the warning message. It's basically telling you that, hey, look into this contingency table that you have. Something seems to be off. And as a matter of fact, it is. You have these areas here in the table that don't have enough observations. We mentioned that in class. So in order for you to run a successful chi-square test, one of the assumptions is that all of these are substantial, like you have values in every one of these. And it notices here that there are some boxes, let's say in the contingency table, that don't have enough observations. That's why you're getting this warning. And as I said, there are other chi-square tests that you could be using, but since we only learn, there are other tests that you could be using, but since we only know the chi-square test, that's what I'm asking to use right now. All right, so that's how this one works. And again, you could look at the observed and the expected and whatnot. Now, if you look closely here, you see again that the p-value is greater than 0.05. So we can fail to reject the null hypothesis. There doesn't seem to be a connection between reading the book or not and the grade that you're getting. Okay. So that was the chi-square test. The second piece is we're trying to figure out how to do hypothesis testing with proportions. And in the example that I have over here, we're informed that 8% of the population are colorblind. And then there's this island in the South Pacific. Look it up. It's a very interesting story. This is called the colorblind island because at least a quarter of all the people there is colorblind. Okay, so in this case, out of the 300 people or 300 something, 66 people are colorblind. And it's very interesting why this is so. As I said, look it up. Very, very fun story. And so what we're trying to figure out now is if the ratio of 26.4% of the population is equal of the population of that island is the same as the general population. And so our null hypothesis is that yes, these two are equal to each other, and the alternative is that they are not. We will do this by hand in a sense, but we can use R, let's say, to do the computations. So first of all, remember that if we're doing, like, this is a one sample proportions test, and what we're doing really is we are trying to figure out what the standard error is using the formula that comes from the a central limit theorem for proportions. And that p over there, we're given that to be 8. And 1 minus p is obviously 0.92. So first, let's calculate the standard error. I think we have 250 people in that island. That's what goes in here in the denominator. So the ratio is 0.0171. So I had a couple of folks ask me, like, is this possible to do in R? And yes, it is. So let's go ahead and just do a simple computation in R. I'm pretty sure you've tried it before, but just in case, let's throw that in there. You can do whatever you want in R. You can name whatever. You can do like whatever computation you want. So if you put SQRT, that stands for square root, and what you need to do is you need to put P times 1 minus P. A good idea is to just set up things like that. Okay, 0.08, I'm sorry. And then inside here, you can just put P times parentheses 1 minus P. All right, so you don't have to specify what it is. And then divide with, again, you can go up here and say n is 250. The reason why I want to do it like that is because maybe later on I want to do more things. Okay, and so if I do it like this, I just need to change the p and the n up there, and you can always compute the standard error. All right, so there you go. You have np, and then, whoops, let me like this. If I compute here, you also get the standard error, which is 0.0171, just like we find here. You can chop off a couple of things, or you can leave it like that. It shouldn't affect the output at the end. Then what we want to find is the corresponding z-score, because again, the central limit theorem for proportions implies that you should be using a z-score. And to do that, we just need to compute the difference between the two proportions, starting with the proportion of the population that we're examining versus the general population, and divide with the standard error that we computed before. And that's one of the reasons why I really like to just do it like this. I could just say, for example, p hat, I don't know, whoops, let's see, let's go over there. You can go and do p hat. This is the population, the proportion in that island. I think it's 26.4 or 0.264. And then we can put p for the population. We already have that. It's 0.08. So if I want to find the z value, I'll just do z equals parentheses p hat minus p divided by standard error. Okay, let me run this real quick. So this way, you don't have to copy things around. You can just keep on doing your computations. And in this case, we got the z to be something like 10.72, whatever that is. Okay. And so that is my corresponding z value for the hypothesis test. And to finish it off, I need to figure out, like, what does that correspond in terms of p-value. So remember, I want to find the probability of z being above that number and below its complement, right? So the best way to do that is just go ahead and straight up compute the p-value to be twice what? Well, you have to do 1 minus p-norm of, what is it? What do we got before? Z, okay? So if I don't put any requirements here, it means standard normal, which it is because we basically did this computation. We converted it to z-scores, and the 1 minus p-norm, remember the p-norm finds you the probability up to that 10 that we computed earlier, and we want the complement. That's why the 1 minus. And then the 2 times, oh, I forgot the times here. The 2 times is just going to double that because we're doing a two-sided test and everything is symmetric. So if I run it, you're getting your p-value. And in this case, it's just going to give you 0. We could go ahead and ask for more decimals to just see what this is. But if you do get a p-value 0, just write smaller than 0.0001. Okay, because basically our jokes on this, like z value of 10 is huge. Okay, and that's basically it. This proportion is drastically different than the 0.05, right? So than the 0.0, than the 8% of the general population, because you look at the z value. I didn't even need to compute the p-value actually, because if you remember, for z more than 3, 4, the probability is extremely low. So for a z-score of 10, you could just safely say, yeah, the probability is extremely low, definitely lower than 0.05, the rejection region. So We reject the null hypothesis. A proportion of colorblind people in this island is statistically different than the general population. And I also give you a link over there to follow with the rest of the story. Okay, so that's all you need with these two tests, the chi-square and the on proportions test, and I'll see you in the next one.